Now we are in homework 11 problem 2. In this problem we have three functions of v. The first one is this, f equals to this, and the second one is this, and the third function is this. So we have these three functions. So now we need to prove or disprove that which function may represent a WSS stochastic process or a spectral density function, or they can represent both. So we need to explain it. So for the first function is this. So at first we change v into tau, and we got this. From this we know that this function should even because it's absolute tau. It should even, and also it's non-negative because this value of the function is no less than 0. So it's even and non-negative. And also we change v to omega, and it's the same. So it's real, and we know that this function is real, and it's more than 0. So it's non-negative. Thus, this function, the first function, it can represent WSS stochastic process, and also it can represent a spectral density function. So that's the first function. The second function is this. The second function is the square of sine v divided by the square of v. So from this is the square of a special element. So this function is even and non-negative. So from we have proved it. So from this, according to the definition, this function may represent both of them. So that's the second function. So now we are in the third function. The third function is a little special. So we change v into tau at first. So when tau is no more than alpha, the value is 1. Otherwise, it's 0. So we can do a Fourier transformation. We transform it in Fourier ways. So we got the Fourier transformation of f tau equals to this. So which is not non-negative. Because this value sine alpha omega can be small, can less than 0, and omega is also can less than 0. So this function may be negative, the value of this function. So f tau cannot be WSS stochastic process. So it cannot be an autocorrelation function. Also now we change v into omega, and we got this form. So for this form, we can set f omega equals to s omega. We assume that it is a spectral density function, and we found this function is non-negative. It's 1 or 0, so it's non-negative, and also it's real because it only related to the absolute value of omega. So no matter the omega is positive or negative, the value of function is not related to the value of omega, so it's real. So thus it may be a power spectrum function. So this is the third function. So that's the whole story of the second problem.